Good day, everyone. Group 4 BSIS2C presenting our final project. So our topic is the Avl Tree algorithm. It is a self-balancing binary search tree. So the Avl Tree is named after its inventors, Georgy Adelson-Velsky and Ivan G. Landis. It was introduced in the 1962 in the research paper called an algorithm for the organization of information. This makes the AVL tree the first self-balancing binary search tree ever created. So a normal binary search tree can become unbalanced if we insert data in sorted order, like this. Inserting data 1, 2, 3, 4, and 5, it will create a long chain. This is called a skewed tree. So skewed trees are very slow because searching becomes like a scanning list. But an AVL tree prevents this by checking the balance factor, the height difference between the left and right subtrees. So if the tree becomes unbalanced after insertion or deletion, the AVL tree automatically fixes itself using rotation. And this rotation can be left rotation, right rotation, left and right rotation, and right and left rotations. Because of this, AVL trees avoid problems like left skewed trees or right skewed trees, where operations become slow. Instead, AVL trees maintain a height of about log base of 2 of n, making operations fast and efficient.
Next, let's talk about the time complexity of AVL3. So the reason of AVL3 performs so well is simple. It's always stay balanced. A balanced tree has a height close to log base 2 of n, which means if even the number of nodes increase to hundreds or thousands, the heights only grow as a little. Here are the time complexity. Searching. The time complexity of searching is O of log n. Since the tree is balanced, we skip large portion of data quickly. Next, insertion. The time complexity of search insertion is O of log n. After insertion a node, the tree checks for imbalance. If needed, it performs a rotation that's only take O of 1 time. Next is deletion. The time complexity of deletion is O of log n. Just like insertion, deletion also triggers balance checking the rotation when necessary. Next is rotation. The time complexity of rotation is O of 1. Rotation are extremely fast.
In our real-world scenario, we use books with numbers to represent how data is stored inside a tree. First, we show what happens in normal binary search tree when books are inserted in order. For example, we insert book 1, then book 2, then book 3, then book 4, book 5, book 6, and book 7. Because the numbers are in sequence, all books are placed on one side, forming a long straight line. This makes the tree unbalanced. A student trying to find book 6. Since the books are arranged in a straight line, the student needs to check each book one by one, starting from book 1, then book 2, then book 3, until they finally reach book 6. This takes more time and the search becomes slow. This is exactly the problem with unbalanced tree. Next, we demonstrate this using the same book's number. But now using AVL tree rules. We insert book 1 and the tree is balanced. We insert book 2 and the tree remains balanced. But when we insert book 3, the tree becomes unbalanced because all books are leaning to the right side. The Avl tree detects this imbalance and fixes it by forming a rotation. After this rotation, book 2 becomes the new root. Book 1 goes to the left and book 3 goes to the right. Now the tree is perfect balance again. Because of this, search become much faster. Instead of checking book one by one, the student can follow the structures of the balance tree, reducing the search steps. This is how Avl Tree helps keep the data organized efficiently in real-world situations. So in this section, we will evaluate the performance of Avl tree compared to a normal binary search tree using our real-world scenario of arranging book by numbers. So our goal is to measure how fast search, insert, and delete operation are when a tree is balanced versus unbalanced. So let's start from a normal binary search tree. So I insert book 1. So book 1 is the root. Then I insert book 2. So since book 2 is greater than book 1, so book 2 is the right child of book 1. Then I insert book 3. So book 3 is goes to the right child of book 2. So continue with book 4, book 5, book 6, and book 7. Each new node goes to the right child, right of the previous one. The final structures is like this. So this tree is completely unbalanced. Search for book 7 requires every book sequentially from 1 to 7, which is very slow. So this tree is completely unbalanced. Searching for book 7 requires checking every book sequentially from book 1 to book 7, which is slow. This demonstrates how normal binary search tree can perform poorly when data inserted in order. So now insertion with rotation. Now let's show how Avl tree handle the same book numbers. So I insert book 1. So book 1 is the root. I insert book 2. So book 2 is the goes to the right child of book 1. So I insert for book 3. So the 3 is become unbalanced. So to fix it, Avl tree perform left rotation. So the book 2 is the root and the book 1 is the left child of the book 2, then book 3 is the right child of book 2. Then insert book 4, so still balance, so book 4 is the right child of book 3. Then inserting book 5, this case another imbalance. So Avl tree perform a left rotation again. So this is the output. So insert book 6. So still balance. So insert book 7. The tree becomes unbalanced. So and perform a left rotation. Now Avl tree is perfectly balanced. Searching for book 7 requires only few steps instead of checking every book like the imbalanced binary search tree. From this demonstration, we observe the three main results. So Avl tree always stay balanced even inserting many books. Searching is significantly faster. Fewer steps are needed to find books, and the rotation maintain performance. So single and double rotation occurs automatically when the tree is become unbalanced. In conclusion, the Avl tree clearly performed better than a normal binary search tree. So it maintained balance, keep the height small, and ensure the search, insert, and delete operation are fast. So our evaluation confirmed that Avl tree constantly maintain O of log and efficiency. So this make the ideal for search world systems such as book catalogs, database, inventory records, and file management system where data frequently change and fast searching is needed.
In our overall discussions, we highlight the following points. In AVL3 are reliable and consistent. They guarantee the fast searching. They prevent the tree from becoming unbalanced. And rotations make the tree self-correcting. Even when many values are inserted in order, the value tree fixes itself. And with real-world data, it performs very well. In our book arrangement situation, the Avl tree keep the book organized, so searching, inserting, and deleting books were always fast.
So this ends our presentation and simulation of the AVL3 algorithm. We hope that our explanation helped you understand how the AVL3 works and how they stay balanced, and why they are useful in real-world applications.